Space fractional constructive equation model for non-Newtonian fluid flow. Non-Newtonian fluid exhibit complex flow behaviors that cannot be adequately described by the simple linear relationship between shear stress, shear stress, and, and shear weight, as, as is the case for Newtonian fluids. Instead, the viscosity changes with the shear, shear rate, and they may also display additional complexities like time dependent effects, yielding, or memory. These fluids are prevalent in many industrial and biological systems, including food processing, petroleum engineering, biomedical applications, and materials manufacturing. The traditional modeling approach for fluid flow is based on the Navier-Stokes equation, which describe fluid motion under the assumption that the viscosity is constant, as case for the Newtonian fluids. However, these equations fail to capture the behavior of non-Newtonian fluids due to their varying viscosity and shear dependent properties. The application of fractional derivatives in the modeling of non-Newtonian fluid flow is particularly useful for fluids that exhibit viscoelasticity like polymer solutions and rheological complexities like polymer solutions uh, polymer solutions like shear thinning or shear thickening. These types of fluid do not behave according to the simple rules of classical fluid mechanics. The space fractional constructive equation model which modifies the traditional equations of motion to include fractional spatial derivatives can thus provide a richer, more realistic representation of this behavior. Applications. Such a model is essential in, in fields where non-Newtonian fluids are commonly including like polymer processing, blood flow, food and cosmetic industries, petroleum engineering. Objective of the model. The primary goal of developing a fractional fractional constructive equation model for Newtonian fluids is to provide a framework that accounts for shear dependent viscosity memory shear dependent viscosity, second one memory and hereditary effects, third one non-local interactions which are often observed in real world fluid systems. By doing so, this model improves the ability to predict the behavior of complex fluid systems, leading the better design to optimization in various engineering applications. Real world applications. The application of space fractional constructive equation models for non-Newtonian fluid flow has far-reaching implications across several industries. These models, by incorporating fractional derivatives, can accurately compl- capture complex time-dependent behaviors and non-local interactions within fluid. Non-Newtonian fluids which do not follow the classical laws of the fluid mechanics are commonly encountered in various fields. There are some key points like polymer processing. Polymer mills and solutions exhibit non-Newtonian flow behavior such as shear thinning or shear thickening, making their modeling complex. The polymer industry understanding and controlling the flow of polymer mills, melt, drying, extrusion, molding, and casting process is critical. The space fractional models are useful because viscoelasticity, memory effects, and non-local interactions. Second one, blood flow in arteries. The study of blood flow in the circulatory system is a critical area of biomedical engineering. Blood is a shear thinning fluid, meaning its its velocity, its viscosity decreases with increasing shear rate. Example: when flowing through narrower blood vessels. In real world applications like blood pressure monitoring, surgical simulations, and arterial health, fractional models are particularly useful because of viscoelasticity of blood, complex complex flow patterns, memory effects, and etc. And also and petroleum engineering, drilling fluids and oil reservoir simulations are key applications in petroleum engineering. The flow of non-Newtonian fluids like drilling muds, which are shear thin fluids, requires advanced models that account for shear thinning behavior. Drilling muds need to maintain a stable flow under varying shear rates during drilling operations, etc. Next one, impact on design. In, impact impact on design. The incorporation of space fractional constructive equation models for non-Newtonian fluid flow into design processes has a significant impact across various industries. These models provide more accurate predictions of fluid behavior, accounting for complex non-local interactions, memory effects, and time-dependent characteristics. By enhancing the understanding of how non-Newtonian fluids behave under different conditions, these models lead to more efficient, optimized, and reliable designs. There are some key points like enhanced accuracy in predicting fluid, fluid behavior. Traditional models those such as based on Newtonian fluid assumptions often fail to predict the behavior of non-Newtonian fluids accurately, especially in scenarios involving varying shear rates or time-dependent effects. And second one, optimization and equipment design. Space fractional models enable engineers to design equipment that is optimized for non-Newtonian fluids. Third one, im- improved manufacturing processes. Sorry, the use of fractional models directly impacts the design and optimization of manufacturing process. The non-Newtonian fluids are used such as in extrusion, injection molding, coating, and 3D printing, etc. Next one, exploring space fractional calculus. Space fractional calculus refers to the refers to the generalization of classical calculus to include fractional derivatives and integrals in the spatial domain rather than just a term, which allows for modeling of phenomena involving long-range interactions and non-local effects and memory-dependent behaviors, unlike traditional derivatives that only depend on the behavior of a function at a single point. Fractional derivatives can capture the influence of a function over a broader region, provide a more general and flexible approach for modeling complex systems. This is particularly useful when the system exhibits anomalous diffusion and non-local interactions or memory effects. Fractional derivatives and space fractional calculus. In space fractional calculus, these derivatives are applied with respect to spatial variables rather than time, and they are particularly useful in modeling systems where interactions occur over long distances over long distances, or when the behavior at one point is influenced by a broader region. These fractional derivatives you are often defined using integral operators like Riemann, Liouville or Capito derivatives, which are generalized the standard derivative to frictional orders. Riemann Liouville Riemann fractional derivatives. D power a f of x is equals to 1 by r of 1 minus a into d by dx integration limits x to a f of c by x minus e of d. Applications of space fractional calculus. Application of space fractional calculus. A. Modeling of non-Newtonian fluid flow. B. Anomalous diffusion. C. Fractals and permeability in porous media. D. Electrochemical systems and battery design. E. Biological systems and medical applications, etc. Real world applications in hydraulic engineering. This is particularly relevant in systems where fluid flow is complex, irregular, or influenced by long range interactions such as in porous media, groundwater systems, river and stream flow, sediment transport, and infrastructure design. The following are some most notable applications: modeling flow in porous media. In hydraulic engineering, groundwater flow and flow through porous media are crucial areas where space fractional calculus has been applied. The movement of water through soil or rock is often non-local and influenced by heterogeneity and, fractality in the medium, making traditional model based on local diffusion inadequate. Application example: contaminant transport in groundwater. In groundwater systems where contaminants are dispersed irregularly, fractional addition advection. The diffusion models can describe the anomalous spreading of pollutants, improving risk risk assessments and cleanup strategies for environmental protection. Second one, sediment transport and erosion. The sediment transport is a fundamental problem in hydraulic engineering, particularly in the design of rivers, coastal zones, and dam reservoirs. The movement of sediment particles is influenced by factors such as water flow, turbulence, and long range interactions among particles. Class- Classically, models often fail to capture the complex and non local dynamics involved in sediment transport. Third one, fluid complex geometries like rivers and channels. In river engineering and the design of hydraulic structures, flow through, flow through irregular channels or man-made structures such as dams, locks, and spillways is difficult to model accurately using traditional methods due to the irregularity of the flow path and the complex interactions between the fluid and the structure. The spacing fractional calculus offers a powerful tool for improving the accuracy of hydraulic engineering models. Advanced advanced modeling advanced modeling for fluid dynamics. Fluid dynamics is a field of physics concerned with the motion of fluids, liquids and gases, and the forces acting on them over time. Fluid dynamics has evolved in the development of advanced mathematical models and computation tools to capture complex behaviors observed in real-world fluid systems. Here are some advanced modeling techniques and concepts used in the modern fluid dynamics. First one, Navier-Stokes equation. With the Navier-Stokes equation are the foundation of classical fluid dynamics. These equations describe the motion of incompressible or compressible fluids and are based on Newton's second law applied to fluid motion. They account for the viscosity, pressure, density, and velocity. The density and velocity of the fluid as well as external forces. For, in, for incompressible flow, the Navier-Stokes equation in vector form are P of dou V by dou T plus of V into delta of V is equals to minus delta P plus U delta square P plus F, where V is the velocity field, P is the density of the fluid, rho is the pressure, nu is the dynamic viscosity, F represent external forces, example gravity. Last conclusion. In the field of fluid dynamics, advanced modeling techniques are crucial for understanding and predicting the behavior of fluids in a wide range of engineering and scientific applications. The traditional approaches such as Navier-Stokes equation form the foundation for modeling fluid flow. However, as systems become more complex, incorporating factors like turbulence, multi-phase flow, non-Newtonian fluids, and anomalous diffusion, and more sophisticated models and methods are required. Models such as Reynolds average Navier-Stokes RANS and large AD simulation LES, and significantly improved the prediction of turbulent flows, while tools like the finite volume method FVM and finite element method FEM. As fluid dynamics continues to evolve, these modeling techniques will remain central to addressing the increasingly complex challenges faced in a wide array of fields, including aerospace, civil engineering, energy systems, and environmental engineering. Thank you.